This lesson is on L'Hopital's rule, and it looks like La Hospital, but there's no S, so it's L'Hopital. It's a French guy who came up with this. And what we're doing is we are working with limits, and sometimes you get what's called an indeterminate form. And an indeterminate form is when you plug in and you get something like 0 over 0, or infinity over infinity, or negative infinity over infinity, versions of positive and negative infinities over each other. But it's an indeterminate form. Again, 0 over 0 is also an indeterminate form. And you'll see when we do examples what we're talking about here. But this is the only time that you can use L'Hopital's rule. The rest of the time you'll be figuring out limits using our standard plug-in, try some algebra, graph it techniques. Okay, now we're going to move on to some examples. Our first example, we're doing the limit as x approaches 0 of cosine of x plus 2x minus 1 over 3x. Now, if you plug 0 in, the cosine of 0 is 1, and then 2 times 0 is 0, and then you have a minus 1. So you end up with a 0 on top. And then if you plug 0 into the bottom, you also end up with 0 in the bottom. So this is an indeterminate form because it would be 0 over 0 when you plugged in. Now, how to use L'Hopital's rule. You want to put an equals mark with a little L. Okay, so you put an equals mark with a little L apostrophe over it, and that way whoever's looking at your paper knows that you are using L'Hopital's rule. The limit stays the same. So limit as x approaches 0. What changes is that you take the derivative of the top and the derivative of the bottom separately. You do not do a quotient rule. This is not a quotient rule. You just look at the top, put its derivative on top, and then the bottom, put its derivative on the bottom. So on top, the derivative of cosine is negative sine. So negative sine here. The derivative of 2x is 2. The derivative of 1 is 0, so I don't need to put that. And then on the bottom, the derivative of 3x is 3. Now, I can plug 0 in and not have an indeterminate form. I can plug 0 in and do something with it. So, I'm not going to put limit anymore. I'm just going to plug 0 in. So, negative sine of 0 plus 2 over 3. Well, the sine of 0 is 0, so that gives me 2/3. So that is the answer to this limit. Okay, let's move on to example 2. We have the limit as x approaches 0 of e to the x plus e to the negative x minus 2 over 1 minus cosine 2x. If you plug 0 in, anything to the 0 power is 1. So you have 1 plus 1 minus 2, so that gives you 0 on top. And then the cosine of 2 times 0 is the same thing as the cosine of 0, which is 1. So you have 1 minus 1 on the bottom, which is also 0. You have another 0 over 0 indeterminate form. And so we're going to use L'Hopital's rule again. So I'm going to put equals with a little L apostrophe over it. Keep my limit. And then take the derivative of the top separate from the bottom. So the derivative of e to the x would be e to the x. The derivative of e to the negative x would be e to the negative x times negative 1. So instead of putting times negative 1, I'm going to change that plus to a minus. That basically accomplishes the same thing. And then the derivative of the 2 is 0, so I'm not going to put anything out there. On the bottom, the derivative of 1 is 0. I bring down the negative. The derivative of cosine is negative sine, so that changes to a positive sine 2x, and then times 2. So since it's positive, I'm just going to erase that because we just need the positive sine 2x times 2. And you could even move that 2 to the front just to make it look pretty. Alright, now if I plug 0 in, I have anything to the 0 power is 1. So I have 1 minus 1 on top, which gives me 0, which is okay. But on the bottom, when I plug 0 in, 2 times 0 is 0. The sine of 0 from our unit circle is 0. and 2 times that would be 0. So again, I have 0 over 0 indeterminate form. Well, the nice thing about L'Hopital's rule is you can do it multiple times. So we're going to use L'Hopital's rule again. Put another equals mark with a little L apostrophe above it. Bring down the limit. And then take your derivative. So the derivative of e to the x is e to the x. And then I have minus. The derivative of e to the negative x is e to the negative x times negative 1. And again, that times negative 1 is just going to change that sign in front. On the bottom, I bring down the 2, and the derivative of sine is cosine. And the derivative of 2x is 2. So again, on the bottom, I'm probably just going to multiply this 2 in the back with that 2 in the front and write a 4 in the front, just so that it's easier to work with. Now, if I plug 0 in, I get 1 plus 1 on top. So I know that I am out of the indeterminate forms. E to the 0 plus e to the negative 0 over 4 cosine 2 times 0. So again, that gives me 1 plus 1 on top. On the bottom, I have 4 times the cosine of 0, and the cosine of 0 is 1. So I have 2 over 4, which is 1/2. And again, this would be the y value that your graph is going to, your original graph is going to at 0. But if you are in a non-calculator section, you wouldn't necessarily be able to know that without using L'Hopital's rule. So I highly expect this in a non-calculator section of your test. But again, you can only use it with indeterminate forms. Okay, our first 2 examples, we had the limit as x approaches 0. Now we have the limit as x approaches infinity. And this, you can look at it and say small over big, and that would go to 0 if you know your toolbox functions, but let's say you didn't. The natural log of kind of infinity is thinking about what's happening as it goes on to the right. If you get bigger and bigger, the answer is going to get bigger and bigger. And the same thing with x. The bigger numbers you get in, the bigger output you have. So you have an infinity over infinity situation. And again, like I said, this is technically small over big, but you may not remember that in the pressure of a test. So infinity over infinity, we can use L'Hopital's rule because it is an indeterminate form. So equals L'Hopital's rule. And we're going to say the limit as x goes to infinity. And this is really interesting because the derivative of natural log is 1 over x. The derivative of x is 1. You're out of the indeterminate forms. Okay? And so if you plug in bigger and bigger numbers here, you get the top approaches 0, so 0 over 1 is 0. Or maybe at that point you realize it's a small over big and it goes to 0. But again, I wanted to do that one because that natural log, you have to remember what its derivative is and how that works. Okay, our next example doesn't look like it's going to fit with L'Hopital's rule because it's not a fraction. And L'Hopital's rule pretty much uses fractions, but what you have to remember is your power rules. And when you have a negative exponent, that is the same thing as moving it to the bottom there. Because e to the negative x times something, I can actually move that to the bottom and make that e to the x on the bottom. And the square root of x on top, you may want to write that, let's erase that and say x to the 1/2, because we know we're probably going to be taking a derivative. Okay, so again, as you go to infinity, and you can think about this being a small over big situation, which would go to 0, but I also wanted to show you that L'Hopital's rule would apply because you may be asked to use it in a situation like this. And so if you go to infinity, you get bigger and bigger numbers on top and bigger numbers on the bottom. So that would be an infinity over infinity situation. It's an indeterminate form. So we're going to say equals and use L'Hopital's rule. Keep our limit notation. and then take our derivative. Well, the derivative of x to the 1/2 would be 1/2 x to the negative 1/2. The derivative of e to the x is e to the x. And then with those power rules, this actually becomes a fraction with just the 1 on top, because that x to the negative 1/2 is going to move it to the bottom. I can move that 2 to the bottom because it's on the bottom of a fraction. So I have x to the 1/2 and e to the x. So if you didn't notice it before, now you should notice that it is a small over big situation, and small over big is 0. For our last example, we are doing the limit as we go to infinity of natural log x over square root of x. And again, it's an indeterminate form because as I go to infinity with natural log, it gets bigger and bigger, and as I go to infinity with the square root of x, it gets bigger and bigger. And these really, honestly, I would have a hard time determining which one grows faster. You know, I would have a hunch, but I wouldn't know for sure without looking at a calculator. So this would be a good place to use L'Hopital's rule. And so I'm going to say equals, using L'Hopital's rule. Put down my limit as x goes to infinity. And take my derivatives. So again, the derivative of natural log x is 1 over x. And the square root, you have to think of it as x to the 1/2, so the derivative would be 1/2 x to the negative 1/2. And then I'm going to move things around to make the algebra work. So I'm not using L'Hopital's rule. I don't put an L prime over it, or an L apostrophe. I'm just using algebra to simplify what's going on. So that 1/2 on the bottom I can flip and multiply to give me a 2 over 1. That x is to the negative 1/2 power, so I can move it up. And that 1 over x is like having x to the negative 1, so it would move to the bottom and just be an x. Now, again, I can use algebra to simplify even more because I have x to the 1/2 on top of x, and when you have bases that are the same, I can subtract the powers. And so I'm just using algebra again. I don't put the L. The 2 stays where it is. X to the 1/2 over x to the 1 will leave me with x to the 1/2 on the bottom when I cancel or subtract my powers. Now I clearly have a small over big situation, and it goes to 0.